what happens if we discover the universe has always existed? Because it might have. We know there's a thing called the Big Bang, but it might have been something that happened in a pre-existing universe. Maybe that's eternal. What does that mean for your sort of picture of a creator? Are we more comfortable with the universe that began, or would we be more comfortable with the universe that had always existed?
Up until the 1920s, everyone thought the universe was essentially static and unchanging in time. Then it was discovered that the universe was expanding. Distant galaxies were moving away from us. This meant they must have been closer together in the past. If we extrapolate back, we find they must have all been on top of each other about 15 billion years ago. This was the Big Bang, the beginning of the universe. But was there anything before the Big Bang? If not, what created the universe? Why did the universe emerge from the Big Bang the way it did?
We are small, finite beings, right, which are just clusters of atoms. As we said before, they're very rare, but we understand roughly how they came to be. And we have a limited amount of time, not actually unfortunately, but because of the laws of nature. Like, the laws of nature forbid us to be immortal. Immortality is ruled out by the laws of physics. What's interesting about, if you look at the basic physics of the universe, going from the Big Bang to where we are today, then the physics is driven by the fact that the universe began in an extremely ordered state. So it was a very highly ordered system. And it is tending towards a more disordered system at the moment. And that's called the second law of thermodynamics. And what we strongly suspect, and I would say no, is that in that process of going from order to disorder, complexity emerges naturally for a brief period of time. So it's a natural part of the evolution of the universe that you get a period in time when there's complexity in the universe. So stars and planets and galaxies and life and civilizations. But they exist because the universe is decaying, not in spite of the fact the universe is decaying. So our existence in that sort of picture is necessarily finite, necessarily time limited. And it is a remarkable thing that complexity has got so far that there are things in the universe that can think and feel and explore it. And I think that is the answer. If you want an answer to the meaning of it all, it's that you are part of the universe because of the way the laws of nature work. You are allowed to exist, or you're allowed to exist for a temporary, or for a small amount of time in a possibly infinite universe. What more do you want? You know, when I see people who go, I want more than that. I want more, there must be more to it. What do you mean? The ingredients in our bodies were assembled in the hearts of long dead stars over billions of years and have assembled themselves spontaneously into temporary structures that can think and feel and explore. And then those structures will decay away again at some point, and in the very far future, there'll be no structures left. So there we are. We exist in this little window when we can observe this magnificent universe. Why do you want any more? There are 2 trillion galaxies in the observable universe. You need to know that the Milky Way galaxy has got 200 billion stars. Most of those stars now we know have planetary systems. We estimate there are something like 20 billion Earth-like planets, or potentially Earth-like planets, in the Milky Way galaxy alone. So if you're asking questions about what is my place in the universe, you need to know those things, first of all. It's a framework within which you can think. I tend to restrict myself to the galaxy. Right. So I do think it's possible that at the moment there's one civilization in the Milky Way.
Wow.
And that's us. And I think that's important, actually. And it goes back to what I was saying at the start about the astronomy and cosmology being part of the framework within which you have to think. If you're looking for meaning, or you're looking for how we should behave even politically, that has a bearing to me. I mean, imagine that we're the only place where there is intelligence in this galaxy. And how should we behave?
Right.
Should we actually, notwithstanding the fact that we're tiny and fragile things and insignificant physically, should we consider ourselves extremely valuable in that respect? Because there's nowhere else where, I would go as far as to say there would be nowhere else where meaning exists. But I think it is a local and temporary phenomenon. I think it emerges. Meaning emerges from configurations of atoms, which is what we are. We are simply that. We're nothing more than that. We're very, very rare configurations of atoms, I think. And so that means that we are, if you go all the way down that line of logic, we are the only island of meaning in the galaxy. Otherwise, you have to believe there's some kind of global meaning, and that's a God type thing. And I don't think that's. I think it's more wonderful and more challenging to us, because we have to take responsibility for it, to say we should operate such that we are it in this galaxy. I'm sure there are other civilizations out there in the universe, because there are 2 trillion galaxies. I just can't believe this hasn't happened in other places. The question is, how often does it happen, and how widely spaced are the civilizations? And I think they're very widely spaced, and I think there may be 1 or 2 per galaxy on the average. But that, as you said, what you said it beautifully. That what else can we think?
Right.
And what else do you want? I mean, I think what it says is you have to take responsibility for all those things, those spiritual things that you think about and the emotional things you think about. You are responsible for that. You are that, right? That, whatever that is, it exists in you, and it will only exist for a short amount of time. If civilizations are common, or even slightly common, then there should be civilizations ahead of us. You imagine the timescales. We've been around as a civilization. Let's give it, say, 40,000 years. I don't know how long our civilization's been around. Let's say that. The galaxy is pretty much as old as the universe. It's 13 billion years worth of time. So the idea that there are no civilizations arose, 100 million years ago, 200 million years ago, 1 billion years ago. And imagine what they'd be like if they'd survived. I mean, we've been around. We've had science for, let's say, since Newton or Copernicus, 500 years at most. And look what we've done. We've gone beyond the solar system with Voyager. We've walked on the moon. We're about to go to Mars, I would think. So we're about to begin colonising our own solar system. It's one of the arguments often used to say there aren't any civilizations out there in the galaxy. It's called the Fermi paradox. Because if you imagine a civilization that's 1 million years ahead of us, they should have written their presence across the sky by now. You should see them. I mean, you'll see us. If we survive 1 million years into the future, actually even a few thousand years into the future, we will be exploring the galaxy. We will have spacecraft that are going to other stars. We will be doing it. So our signature will become visible, I'm sure, if we last. There is an argument as well that technology so advanced would be difficult for us to detect. I mean, we tend to think of when you say written across the sky, I suppose it's true. I'm thinking of starships and things like Star Wars, right? Big energy things that you can see the signature of. But actually, it may be that the civilization just becomes a nano civilization, tiny little nanobot, because that's more efficient. It's a better way to do things. So it's possible, I suppose, that there are space probes all over the place that are so small and are so efficient and use so little energy that we just don't see them. I suppose that is possible. So there is no other planet we can go to other than Mars. You can't go to Jupiter or Saturn, you can't go to Mercury or Venus. So if we want to go somewhere and expand our civilization, it has to be Mars. And everything's there that you need. It's interesting, actually, because we know something about the history of Mars now, quite a lot about the history of Mars. And it's certainly clear that there was water, almost certainly oceans, rivers. And that water is almost certainly still there. So there's certainly ice. There may even be pockets of liquid water below the surface somewhere. So couple that with all the minerals and the resources that we know are there, and you have everything you need. So that's the thing about Mars. It's quite nice relative to everywhere else other than the Earth. You can't go to Venus, right? You just melt. It's, 400 and something degrees and 90 atmospheric pressure. I think there must be, even in the solar system, I would not be surprised if we find microbes on Mars or on some of the moons of Jupiter or Saturn where there's liquid water. And the reason is, if you think about, the reason I think that, and it's a guess, is because if you look at the history of life on Earth, so Earth formed, there was no life, it was a ball of rock. And almost as soon as it cooled down, we see evidence of life. So certainly 3.8 billion years ago, possibly even further back than that, we see evidence of life on Earth. So somewhere along the line, geochemistry, active geochemistry became biochemistry on Earth. And we have some idea, that if you get gradients of temperature and acid and alkaline and the conditions that are naturally present on the surface of oceans, then complex carbon chemistry spontaneously happens. So we know that life, almost certainly we know that life began on Earth. I mean, the other option is it came from space or something like that, but it probably didn't, right? It probably began on Earth. So that means that at least here, that happened. And that we know that the conditions that led to the origin of life on Earth were present on Mars 4 billion years ago. And we know that they're present on Europa today. I don't see that there's anything special. Life is just chemistry. The idea that geochemistry becomes biochemistry is not fanciful because it happened here. So I think that given the same conditions, it would be surprising to me if the same thing didn't happen, in that life begins. To test that is one of the great frontiers of science now. It's one of the great challenges, which is why another reason we're interested in Mars, because we know those conditions were there. We know there were what's called hydrothermal vent systems on the floors of oceans on Mars 3.8 or 4 billion years ago. So it would be good to know if what I've said is right. And the way we find out is to find life or evidence of past life. There's a theory called the Grand Tack theory. So it's very hard to explain the evolution of our solar system. When you do computer models of solar systems, you don't tend to get 4 rocky planets too close to the sun and 4 big gas giants further out. And one of the current best theories, and I say this because it shows you how lucky we might be, is that Jupiter, they tend to form these big gas giants and migrate inwards towards the star. So in almost all the computer simulations, just because you've got this big gas giant orbiting in all the dust around the star, they tend to drop inwards. And it looks like Jupiter did that. So it looks like it formed and came in almost to where Mars orbits today, and cleared out the region around Mars, actually, which is maybe the reason Mars is so small compared to the other, to Venus and Earth. But then Saturn was coming in as well. And in the computer models, the interaction between Jupiter and Saturn stops Jupiter coming in before it gets to the Earth. And they both get dragged out again. And so to where they are today.
Oh, wow.
And so that seems to be, it's one of the best theories for the evolution of our solar system. So what are the chances? The chances of that are so minuscule, like tiny. So that's the thing, I think, about these rocky planets. In order to get a civilization on them, I think you need quite unusual solar systems. And that would be a guess. And you need quite unusual stability on the planet for billions of years. And that's why I think we might be quite lucky. Then we didn't know of any planets beyond our solar system because we hadn't detected them. So even if we thought, well, we can't be special, we didn't know. And then in the early 1990s, we started being able to detect planets. And now we've detected well over 3,000. We've got missions up there like the Kepler telescope that are just trying to detect planets. So thousands of them. So now the statement is that pretty much every star in the sky will have planets around it, which is remarkable. If you go out, it's a clear night, you go out and look at stars, you can imagine that there will be solar systems around everyone. So that allows us to start thinking how many potentially Earth-like planets might there be in the Milky Way galaxy. And the answer is about 20 billion. What you mean there is a rocky planet, the right distance from its star, possibly, if everything's right, to have liquid water on the surface and so on. In a nice distance from the star, perhaps 1 in 10 stars. We talk about a thing called the habitable zone. Now, in the solar system, there are 3 planets in the habitable zone. There's Venus, Mars, and Earth. Venus is close to the sun, Mars further away. All of those planets, though, we think had water on the surface. So they all could have been habitable in that sense. And still, we're looking for life on Mars to this day. The flip side of this is there are loads of planets out there, and there's been loads of time. This has got a name, actually. It's called the Fermi paradox, after someone called Enrico Fermi, a great Italian physicist, who asked this very simple question, which is, where are they? Because given the number of planets, given the number of stars, and given the amount of time in this galaxy for complex life to emerge, it seems as if at least a few civilizations should have become a spacefaring civilization. So part of the evidence, part of the great conundrum here is that, so on the one side, yes, we've got the history of life on Earth, which says that we took a long time to emerge. And so it looked quite like an unlikely process. On the other side, you've got all this real estate, and you have this, so if you think about where we could go, what could we become as a civilization? So already we are becoming a spacefaring civilization now very quickly. So give us 1,000 years. We don't destroy ourselves or do anything stupid. I'm sure we're going to be on Mars. We're going to be on the moon. We're going to be thinking, perhaps, taking our first steps out to the stars. Give us 1,000,000 years, 1 million from now. If we survive, we should become a spacefaring civilization. Now, 1 million years. The galaxy has been around for the age of the universe, 12, 13 billion years. So it only takes a few civilizations to have evolved a bit ahead of us. 1 million years. Well, let's say 1 billion years. 1 billion years, it's still nothing. You get some civilizations that evolved 1 billion years before us. Why can't we see them? So then people start saying, well, maybe there's a finite life that all civilizations have. Maybe they destroy themselves. Maybe they don't become spacefaring civilization. What's interesting is when you talk to astronomers, they say that we estimate there are 20 billion potentially Earth-like planets out there in our galaxy. Surely there must be life all over the place. Right, it's a guess because we haven't found any anywhere. But what we know from the history of life on Earth is that life began pretty much as soon as it could here on Earth. So we have good evidence that life was around, let's say, 3.8 billion years ago. So pretty much as soon as the Earth had formed and the oceans formed on the Earth, you see evidence of life. So that might give you a sense that the origin of life on a planet might be a high probability, right, given the right conditions, just because of what we see on Earth. But this is really important. Well, when did complex life appear? So not just single cell, animals and plants. And the evidence of complex multicellular things on Earth goes back, let's say, 600 million years or so, not much further than that. So it's within the last billion. So on Earth, what happened was that there were single-celled things doing interesting stuff, photosynthesis and things, but for let's say 3 billion years from the origin of life, nothing else, not much going on. Slime. The last billion, 500 million-ish, right? Do you see complex life? So it took around a third of the age of the universe on Earth to go from the origin of life to something that can think. The star was stable and didn't run out of fuel, and the orbit of the planet was stable. It didn't get hit by too many asteroids. So I think that if you start asking for stability for billions of years, if that's what it takes, typically, to go from the origin of life to something that can think, then there are very few places indeed. There's a thing called the eukaryotic cell, right, which is what we're made of. And every complex living thing on the planet is made of. Every plant, every blade of grass, every insect. So it looks like those things evolved once on this planet. What happened is one type of more primitive cell, a bacteria in this case, got inside another kind of cell called an archaea, got inside and didn't die, and somehow managed to multiply like that. And it looks like that's the origin of all complex life on Earth. So when you see things like that, when you start seeing the things that had to happen to make us, you start to think that this place may be extremely special. And you can make the argument, and I do actually, I think it's very important politically as well, that this could be the only planet in our galaxy currently that has anything on it that can think. If we are the only planet currently in the Milky Way where brains exist, where conscious thought exists. We are the only place where meaning exists in a galaxy of 400 billion stars. Imagine if we decide to press the button tomorrow, nuclear war, right? We press the button. The person who does that might wipe out meaning in a galaxy. Yes. So we look out into the universe and we see that there's a lot of stuff there that's interacting gravitationally, but is not interacting strongly with the matter out of which we are made and the stars are made. So it's almost certain that that's some form of particle, that fits beautifully. And we see lots of different observations of the way galaxies rotate and interact, and even that oldest light in the universe, the so-called cosmic microwave background radiation, we see the signature of that stuff in that light as well. So we think that there's some other particle out there. And to be honest, we thought we would have detected it, I think, at LHC. We have lots of theories called supersymmetric theories that make predictions for all sorts of different particles that would interact weakly with normal matter. And I think it's broadly seen as a surprise that we haven't seen them at LHC. So that just may well mean that either they're a bit too massive, so we need more energy to make them, and we just haven't quite got enough, or we're not making enough of them often enough to see them, which is one of the reasons we're upgrading the LHC. So we also look for them, by the way, directly. So we have experiments under mountains. We bury them under mountains so the cosmic rays from space don't interfere with them. And we're looking for the rare occasions when these dark matter particles bump into the particles of matter in the detector. Because the idea would be this room's full of them. I mean, the galaxy is swimming with dark matter as far as we can tell, but it interacts very weakly with this matter, so it doesn't bump into us very often. So we're looking for the direct detection of it, and we're looking to make those particles at LHC. So it interacts through gravity, and the archetypal particle that's everywhere that doesn't interact strongly is a neutrino. So we do know about neutrinos, we've detected those. And there are something like 60 billion per centimetre squared per second passing through your head now from the sun. So they get made in nuclear reactions in the sun. But they go straight through your head, and they're actually straight through the Earth, pretty much. Occasionally one of them bumps into something. And we can detect those because there are so many of them going through. But we only detect, I don't know, 1 or 2 a day. Yeah, so it's 5 times as much matter is dark matter than is normal matter. And the number is 25% of the universe. So roughly speaking, about 5% of the universe is normal matter, stars and gas.
25% is dark matter.
Yeah, so 5 is normal matter, about 25 is dark matter, and about 70 is dark energy.
That's the other thing.
The other thing
about.
Yeah.
Yeah. So what the hell's that?
Don't know. Know what it does. So again, if we go back, we talked about Einstein's theory earlier. So Einstein's theory, which works spectacularly well, says that if you put stuff into the universe, as we said before, then it warps and deforms and stretches. And it very precisely tells you, given the stuff that you put in it, how much does it stretch and how does it stretch. And the measurement we have is how it's stretching. So we observe, the thing we observe is how the universe is expanding and how that expansion rate is changing and how it's changed over time. So we have very precise measurements of that. So then we can use the theory to tell us what's in it, given that we know how it's responding to that stuff. And that's how we discovered dark energy. So we notice that the universe's expansion rate is increasing. So the universe is accelerating in its expansion, which is exactly the opposite of what we thought. Now, this is in the 1990s that we discovered that. Einstein's theory, which works spectacularly well, says that if you put stuff into the universe, as we said before, then it warps and deforms and stretches. And it very precisely tells you, given the stuff that you put in it, how much does it stretch and how does it stretch. And the measurement we have is how it's stretching. So we observe, the thing we observe is how the universe is expanding and how that expansion rate is changing and how it's changed over time. So we have very precise measurements of that. So then we can use the theory to tell us what's in it, given that we know how it's responding to that stuff. And that's how we discovered dark energy. So we notice that the universe's expansion rate is increasing. So the universe is accelerating in its expansion, which is exactly the opposite of what we thought. Now, this is in the 1990s that we discovered that. We can work out what sort of stuff and how much of that stuff you need to put in the universe to make that happen. And that's where we get these numbers from. One of my friends at Brian Schmidt got the Nobel Prize for that. And I remember I talked to him and he said, he was a postdoc, I think, at the time, so a young researcher. And he was making measurements of supernova, the light from supernova explosions, which are so bright that you can see them, hundreds of millions, billions of light years away. And he noticed that if you look at the data, the light is stretched in the wrong way. So we look at the stretch of light as it travels across the universe, and the universe is expanding, it stretches the light, so it changes the colour. And he noticed that there was a discrepancy which said that the expansion rate is speeding up. It's been speeding up for, I think something like 7 billion years or so, it's been speeding up. So he thought that he's done something wrong, because so he checked it and checked it and checked it, and he couldn't find anything wrong. So he did what a good scientist does, which is he published it so that somebody else could find out what he'd done wrong. And he said that he thought it would be the end of his career. He thought he'd be a laughing stock, and he got the Nobel Prize because he was right. It is stretching.
Wow.
It's a great lesson. It means that if you're sure that you can't see what you've done wrong, then you publish it. It goes back to that thing about humility we talked about earlier. What we're not trying to be right. We're trying to find out stuff. And so a good scientist will be really happy if they turn out to be wrong because they've learned something. Well, it's interesting because it's allowed in Einstein's theory, and it was in Einstein's original theory. So it's got a name. It's called the cosmological constant, and that's it's just allowed in the equations. And Einstein actually introduced it initially because Einstein's equations strongly suggest that the universe is expanding or contracting and not just sat there. So even before we'd observed anything, Einstein had a theory that suggested that the universe is just not static, and actually it really strongly suggests that there's a beginning, right? So the theory itself on its own suggests that you can see that if the universe is stretching today, then it must have been smaller in the past, right? Everything must have been closer together, let's say that. There's a man actually called Georges Lemaitre who worked independently of Einstein, but at the same time in the early 1920s, before we even knew there were other galaxies beyond the Milky Way. And they noticed that the equations suggest the universe might be stretching. And so he wrote to Einstein and said, your theory suggests there was a day without a yesterday. Because he thought, if everything's expanding now, then it must have been closer together in the past. And so there might be a time when it was all together. And he was a priest.
Wow.
So he was a Belgian priest. So I think, I mean, I wrote about this, now it's kind of my interpretation of it, but I think that he was more predisposed to accept what the equations were telling him, because a beginning, an origin for a priest is really a nice thing, because it tells you the creation event.
Yeah.
And Einstein tried to dodge it and put this allowed term into his equation, which is almost the stretchy term, to say, well, if it's all kind of contracting or something, can I put something in to make it stretch a bit to balance it all out so it can be eternal? So, and you can't make it eternal that way. But he tried it. Then he took it out and called it his biggest blunder. Some people think what he'd done was miss the prediction of the Big Bang, really. So by trying to fiddle around to have a static universe that's stable, he missed what the equations were screaming. His own theory was screaming to him, which is that, no, the universe expands or contracts. And he missed it, right? So I think that's probably what he meant by biggest blunder. But in any case, he took it out. And then later, in the 1990s, it turns out that, no, it's there. But it's really small. It's tiny, tiny effect. But it's still dominating the universe now. And it will dominate even more in the future. So we think that we're in a universe that will continue to expand, essentially doubling in size on a fixed timescale, which is about 20 billion years. So we think every 20 billion years into the future, forever, unless something happens, the universe will continue to expand and double in size.